talking about Nijenhuis geometry, my favorite topic for several last years, and this is a project with Andrei and Vladimir Matveev. You will see that the first part of my talk will be, it's like a lecture for students, like a textbook. And the other part it will be devoted to some applications to geodesically equivalent metrics and some integrable PDEs, infinite dimensional system. That's when we started to discuss this topic. I will start with very basic definitions. So the first definition is, of course, a definition of a Nijenhuis operator, the main subject of in this area. So this is a field of endomorphism. So you can think of it as so you can think of it as a tensor field of type 1,1. It's given by just a matrix in local coordinates, and this matrix is it's not a form but a linear operator. So this linear operator must satisfy one additional condition. So this condition here, which means that the Nijenhuis torsion of this operator vanishes, and basically what is written here, it's the only differential condition you can impose on the tensor of type 1,1. I will refer to this object as Nijenhuis operator. So just field of endomorphism satisfying this condition. This definition is differential geometric. So this condition is differential and geometric, and the other definition is purely algebraic. So we consider an operator. You can think of it as a square matrix of size n by n, and we will say that is GL regular. No, GL regular means that I won't consider this operator from the algebraic point of view as an element of the Lie algebra GL and R. And I want this element to be regular. Regular, so meaning that if you consider the orbit of this element with respect to the standard adjoint representation, this orbit must have the maximal dimension. If you are not familiar with this kind of concept, it's not a problem. So there are equivalent definitions which are very simple. So one of them is as follows. So there should be vector xi such that if I consider xi, apply this operator to xi, then once again, and so n minus 1 times. So then I will get vectors which are linearly independent, and so they form a basis in our n-dimensional space. Or you may say it's equivalent, so if I take operators identity L and so on, so L power n minus 1, they are linearly independent, and they form a basis in the centralizer of L, and they generate the space of all matrices commuting with L. One more equivalent definition. So if you consider eigenvalue of L, then this eigenvalue may have arbitrary algebraic multiplicity, but the condition is there should be only one eigenvalue.
Can I ask you one question?
Yes.
So the almost complex structure is not this one.
Second?
The almost complex structure.
Almost complex structure is not of this kind. No, absolutely not. Unless in dimension 2. Dimension 2 it is regular. Okay, and finally, it doesn't matter whether this L is semi-simple or contains Jordan block. So it can be, in any case, it can be reduced to the very nice canonical form, which is known as first or second canonical companion form. I will remind the explicit form a little bit later. That's one part of the story, and now in the title of my talk I mentioned symmetries and conservation laws. In this context, the definition is as follows. Now, let's consider just arbitrary operator. By the way, when I say operator, In my talk, I mean operator defined on a manifold. So that's operator which depends on a point. So this is in field of endomorphism. Okay. So we have a manifold, we have an operator defined on it, and what is a conservation law? To be honest, first myself was a little bit confused and with this definition, but I will explain what it means in a moment. But formally, the definition is as follows. So what is a conservation law for an operator? So this is a function such that, so if I consider the differential of this function and apply this operator, what is called adjoint operator to this differential, because differential it's not a vector but covector. Okay. So then that I will get again the differential form, and I want this differential form to be closed. Everything is local, so the closeness of this form, so it will mean the existence of a function g such that so dg equals a star df. Sometimes the terminology is different. Sometimes one says that f is it's the density of the conservation law. And sometimes one says that the differential of f is conservation law, but it doesn't really matter. So for us today, so f is a conservation law if this condition holds. And so symmetry. So what is the symmetry? It is an operator field. So take another operator field B. We will say that B is either strong symmetry or just symmetry if the following condition holds. So B algebraically must commute with A. No, it's just matrices. So and strong symmetry it means that this condition here so is fulfilled. If you compare this condition with the definition of the Nijenhuis operator, it's basically the same, but if I replace B with A, I will get exactly Nijenhuis torsion. But what is written here is still a very good expression which makes perfect sense if A and B commute. If they do not commute, then what's written here is not so nice, but this is one half of the so-called Nijenhuis bracket for two fields of endomorphisms. So this definition is due to the Nijenhuis. So this is strong symmetry if this expression vanishes, and just symmetry if it vanishes not for arbitrary vectors psi and eta, but for psi, meaning that the symmetric part of this bracket vanishes. Okay, so now still I need to explain the meaning of these two definitions, and maybe I will start with something very familiar to everybody. So consider, instead of an operator, consider vector field. My operators will be associated to a dynamical system, but infinite dimensional. So let's consider finite dimensional case. Take vector field psi and consider the corresponding dynamical system on our manifold generated by this vector field psi. It's just the same. So sometimes when I give lectures to my students only groups, I always say that dynamical system or vector field or flow, it's just the same thing. Yeah. Okay. This is now. So what is first integral? The first integral of psi, obviously, so this is the function such that the derivative of this function along psi is 0, or the Lie derivative is 0. So what is the symmetry of psi? So symmetry of psi. So this is another vector field, say eta, such that psi and eta commute with respect to the standard Lie bracket, or which is the same that the Lie derivative of eta along psi is tends. So there are some properties of first integrals and symmetry fields. They are somehow related to each other. Not just I want to mention a couple of them. So if I consider the symmetry and the integral, so then if I multiply them, so if I consider product f and eta, so then it is still symmetry, and if I apply this eta to f, along eta, so then I will get an integral. Or if I have k the linear independent symmetries and consider linear combination with certain coefficients, so then this linear combination is again symmetry if and only if the coefficients are first integrals. I mentioned all these two properties because we were going to observe something similar, but in the context of the symmetries and conservation laws. For these operators. And that one more remark. No, that's what I've just said. This is a formal analytic condition. But in reality, or so geometrically, or maybe dynamically, so this means the following. So if what is this dynamical system? Dynamical system describes evolution of a point on the given manifold. So I take a point, and u0, so initial condition, so I have vector field, and under the action of this vector field, this flow, this point u0 moves, it evolves, and I can consider trajectories of this vector field. And function f is first integral, the if and only if it is constant under this evolution. So that's everybody knows. And the symmetry fields. So symmetry fields means I would prefer the following definition. So I have two fields, so xi and eta, and if eta is a symmetry of xi, then I can construct a surface, not just one curve here, but the surface depending on t and s, such that the derivative with respect to t is xi and derivative with respect to s is eta. No, but it's just the same as to say that the flows of xi and eta commute. In the context of linear operators, the situation is quite different, but we will need to slightly change the rule of the game. So now, as a dynamical system, we will be considering the infinite dimensional dynamical system defined by this operator. So this is so-called quasi-linear system, the very well known and studied object in geometry and mathematical physics. But so now it's what kind of evolution this equation describes? It describes evolution of curves. So if I instead of initial point, I will now consider the initial curve here, u0 of x. X is a parameter on the curve. And then this system of PDEs describes the evolution of this curve. So there are very many different evolutionary systems. So this is perhaps the simplest one. So I have here I have my initial curve. And then, so for this curve, I can consider the velocity vector, and then I apply this operator to this velocity vector, and this vector, so this direction, shows me how this particular point of my curve evolves, like this. And it happens exactly the same to each point of my curve, and in this way I get the evolution. So what is conservation law? Conservation law in this context is just a function such that that condition I mentioned is equivalent to the following identity here. So it means that if I consider now its function on the space of curves, it's functional with f so being the density of this functional, and then this functional is preserved. So this integral does not change under evolution. So that's exactly what the definition means. And then symmetry means that so if in the space of curves I can find not a curve but surface in terms of the parameters t and s, or you may say that there is a function which depends on three variables t, s, and x, so such that the evolution with respect to t is defined by operator a, and the evolution with respect to s is defined by the operator b. Also, we can say that these two quasi-linear systems are compatible in the sense that if I consider any initial conditions, I will be able to find a solution simultaneous solution for both equations. So it's just infinite dimensional analog of the situations very familiar to all of us. But let me emphasize that this system of PDEs, it's infinite dimensional dynamical system, but everything we need is described in terms of finite dimensional objects like operators, vector field. We don't need to mention this interpretation to develop a theory of symmetries and conservation laws for fields of endomorphisms. Okay, so what we want? We want to study conservation laws and symmetries for Nijenhuis operators, properties of them, and applications. Okay, so now let's start. First, now that I want to present a series of results about conservation laws and symmetries. All of them are not so difficult to prove, but it needs to be done. Just to, if you want to develop any kind of theory, so there should be some background, and that's what I'm going to present now. The first result is a splitting theorem. Which says the following. So, okay, so consider the Nijenhuis operator L. So L is Nijenhuis operator, and assume that its characteristic polynomial splits into a product of two polynomials without common roots. One polynomial is a product of two. So then the no common roots is essential condition, of course. So then there exists a coordinate system, U, V, so we can partition my coordinates into two parts, U and V, in such a way that...
Can I ask another question? So could you give me some example of the situation where Nijenhuis operator appears?
Example of an operator.
Yeah.
Just an operator example. Yeah.
Yeah, just the occasion where it's
Look, you mentioned already one example. This is symplectic, a complex structure. But complex structure is an operator with constant eigenvalues, right? This is the point. For Nijenhuis operators, eigenvalues are not necessarily constant. And if all of them are different, so then the Nijenhuis operator will look like this. It will be just a diagonal. You can reduce it to diagonal form, and moreover, so this diagonal form will be of this kind. So some function which depends on the first variable on the diagonal, some function which depends on the second variable, so and so on. So it is diagonalizable, and so moreover, each diagonal element depends on its own coordinate. And this is what I've just said. This is the beginning of the story. This is a theorem proved not by Nijenhuis. It's known as Heintius theorem. As far as I understand, both Nijenhuis and Heintius were also PhD students of Schouten and worked more or less on the same topic at the same time. So then this is you may think of it as analog of Darboux theorem for Poisson structures. So if your Poisson structure is very simple, so no singular points, so then you know that it's dpdq plus some some kernel is the same. And you may say, okay, but if all of them are very simple, what we are going to discuss? Like in Poisson geometry, we basically want to discuss global properties and singularities, where the eigenvalues collide or some algebraic structure changes. So from this point of view, the complex structure is quite special. And it's basically, it's not what I have in mind thinking.
Okay.
Could I perhaps ask a question? It's rather on one of the previous slides, but so in terms of quasi-linear systems, what does the Nijenhuis condition mean?
They are integrable then. Not just because they admit many symmetries and conservation laws. So then the splitting theorem, so then everything kind of splits into direct product. Nijenhuis operator is direct product of two independent operators depending on the first one depends on the first group of variables, the second group of variables. It's a direct product. Every conservation law is the sum of two conservation laws. The first relates to L1, so the second relates to L2, and the same for the symmetries. So symmetries also split in the most natural way. Good. So this, for instance, so this immediately allows us to describe symmetries and conservation laws for diagonal operators. So if you take diagonal operator, then everything is very simple. All the conservation laws are sort of like this. Oops. So just functions. Sum of functions depending on and function each depends on one variable. Very simple, and symmetries are the diagonal matrices. It's also very simple elements on the diagonal here.
So you're considering this operator as a linear vector field?
Hmm?
You're considering this operator as a linear vector field, or what is the conservation law for operator?
Sorry, I don't quite understand what you want to say.
I thought the conservation law and
Yeah.
symmetry are something about vector field.
But this case, so that I gave a definition of conservation law for an operator. So this is a function. It's satisfying certain conditions. And I say that in this case, this function is very simple. It should not be surprising because if you know how to reduce your operator to canonical form, then for this canonical form you can describe it. So next situation. So let us consider operators which are to GL regular. So satisfying the algebraic condition I mentioned. So then the first result is it's a very kind of universal normal form for all GL regular operators. It doesn't matter so how eigenvalues to behave. They may collide, so this operator may be simple, may contain Jordan blocks, or at a given point you may have just one Jordan block and neighboring points, so everything splits in a very complicated way. So it doesn't matter, so in all cases you can reduce this Nijenhuis, it's a very important condition, to the one of so these forms, so to called, so first companion form and second companion form. So here, so these functions, so here either in the first row or first column here, so these are coefficients of the characteristic polynomial. So what is important here, and maybe so if anybody could give me an advice, I would be very grateful. So here it's real analytic case, and we still have no idea whether the same result holds true for smooth Nijenhuis operators. And just because to prove these results, we used Cauchy-Kovalevskaya theorem, and so how to deal in the C-infinity case, it's still a problem for us. So the next, the symmetries for GL regular Nijenhuis operators. Again, I want to emphasize this, that we consider the situation. We have in mind the situation of singular poles where eigenvalues may collide or something kind of bad that may happen. But if we deal with GL, the regular operator, so then the following general theorem holds. So consider just arbitrary symmetry. So since of GL regular operator. So since by definition M commutes with L, so M can be written as polynomial of L with certain coefficients, and this representation is unique. So what we need to do, we need just to understand something about these functions, some conditions which guarantee that M is symmetry. So then we have the following theorem. No, first of all, first statement. Every symmetry of L is strong. So this is the first we've been surprised with this fact, because for if the operator is not Nijenhuis, it's not true. So symmetries, it's one story. Strong symmetries, nobody seemed to discuss them at all. Next property. So if you consider two symmetries, then the product of two symmetries is again a symmetry. And in particular, all symmetries, they form algebra with respect to the usual matrix multiplication. So next, if you have two symmetries, then this kind of Nijenhuis bracket is zero. It's also meaning that they are symmetries of each other. and in particular, M1 with respect to this bracket commutes with itself, so this M1 is, each symmetry is still Nijenhuis operator. And now about this condition too. All local symmetries of my operator L are in one-to-one correspondence with the systems of first companion coordinates, in the sense that these coefficients here of this expansion are first companion coordinates for L if and only if M, so this operator is a symmetry. The next result, it's something about conservation laws for Nijenhuis operators. So the first property which is well known in this context. So the conservation laws for Nijenhuis operators, so they generate a hierarchy of conservation laws. In the following sense, so let F be a conservation law. So then this condition holds. So the form L star df is closed. So then it follows that all these forms are closed, and therefore, so each F generates the sequence of conservation laws, say F1, F2, and so on, so defined in this way. So we can construct many of them. So one more definition here. We will say that conservation law is regular if the take first terms of this hierarchy if the differentials of first n functions are linearly independent. We will say that f is regular. Now the theorem. The first statement. Every conservation law of Nijenhuis operator is conservation law for all of its symmetries. So all of them, they possess the same conservation laws, basically. And the regular hierarchy of conservation laws are in one-to-one correspondence with the systems of second companion coordinates, in the sense that if you have a regular hierarchy, it will be regular if and only if the first terms, first elements of this hierarchy are exactly second companion coordinates for L. And this shows that first and second companion forms, it's indeed something very important because they are closely related to at least the symmetries and conservation laws. Now, some explicit parameterization. It appears that both all conservation laws and all symmetries can be described explicitly if I know just one the regular symmetry. So the statement is as follows. No, first of all, regular symmetries in the real analytic situation, so real regular symmetries and regular conservation laws, they do exist. I say centered at P. Centered at P means that the symmetry equals zero at the given point. It's very easy to achieve this condition just by subtracting from U certain polynomial depending on it's not a big deal. So then the statement is that so if you consider this expression here, look, so V1, this is an analytic function, which can be applied to symmetry U. So what's written here? So it's just an operator which depends on n functions of one variable. Statement is that M is a symmetry, and moreover, each symmetry can be written in this way. So if you know just one symmetry, then any symmetry can be written by means of n functions in one variable. For the conservation laws, the situation is sort of similar. So if you have just one single conservation law, so then any other conservation law can be obtained in this way. You just take F and apply all symmetries. Symmetries are given here. And in this way, you will describe all conservation laws. So we know tools to start computing. So if you have a particular example, so then you can take it and compute all conservation laws and symmetries. I explained how to do it for diagonal operators. For Jordan block. For Jordan block, the situations, maybe I will very briefly say something. So, so this slide is just to say that for the Jordan block, Nijenhuis Jordan block, the description of conservation laws and symmetries is absolutely explicit. It's not problems. There is a formula which explains everything. Okay, so now the one more remark. You see that symmetries and conservation laws, they possess very many natural properties. I just summarized all what we've just discussed. My next remark is about this GL regularity condition. How important it is. Yeah, it is. No, of course, Nijenhuis condition is important because if the operator is not Nijenhuis, it just makes no sense at all. And GL regularity is also important because, so here is an example. So if you consider that this is Nijenhuis operator, very simple, but not GL regular, so there are two Jordan blocks, two eigenvectors with zero eigenvalue. You can easily describe all the symmetries. They are of this kind. You can describe all conservation laws. You can describe all strong symmetries, and you will see immediately that these nice properties I just mentioned. So GL regularity is important. Okay, now let's talk about some applications. Applications where? In those topics where Nijenhuis operators naturally appear, they naturally appear in particular in the theory of geodesically equivalent metrics. And that's geodesically equivalent metrics. Well, this is something to do with finite dimensional integrable system because geodesic flows of such metrics are exactly what we know as finite dimensional integrable Hamiltonian system. Definition. Two the Riemannian or pseudo-Riemannian metrics are called geodesical equivalent if they have the same geodesics as unparameterized curves. So they have the same geodesics, and the Nijenhuis operator, if you have two forms, then you can hook up an operator out of them. But in this case, this needs to be done in this way. So if you consider this, what's written here, it's the same as to say that if I have an inner product, that any other inner product is defined by means of self-adjoint operators. But there should be some factor here, and this factor is important in order for L to be Nijenhuis. So this formula defines a Nijenhuis operator, and that was discovered by Sinyukov, the mathematician from Ukraine, from Odessa. And so why it is nice? Because in terms of this operator, geodesic equivalence condition can be written in a very nice form. So this is a very simple equation which involves, here you see is L, and nabla is the Levy connection of the metric G. And it appears that if you want to study geodesically equivalent metrics, so G and G bar, it is much better for many reasons to study the pair G and L. So G bar so can be reconstructed from L immediately. This equation is, you see, it's linear in L.
Sorry.
And, yeah.
Can you make some comment on this exponent? Why does that particular exponent should appear here?
I can't make it immediately, so that we can discuss. So this is, you know, for myself, it's just I know that this is a good idea, and I know how to prove it. So how to prove that this factor is important. There is a conceptual explanation for this. No, but me, I sort of kind of user of this theory, not the author. Okay. No, but of course, that was very clever observation, which so can be, as I said, conceptually interpreted now. It's kind of, basically, let me say it in this way. When you do this theory, the natural objects to be considered are not tensor fields, but weighted tensor vector fields. So you need to use some volume form with certain power. And then these objects are much more natural. Then this is the reason. Okay, we will say that G and L are geodesically compatible. So if this condition holds, and there's this definition here, geodesic compatibility and geodesic equivalence. So this is basically the same thing. Now the question: if you want to study geodesically equivalent metrics globally on global manifold, closed manifold, then you will have to deal with singularities. So what is a singularity? It's like in finite dimensional integrable systems. There is a Liouville theorem which says that everything is very nice, almost everywhere, but the most interesting events happen at singular points. What is singular point in this context? So singular point is a point where something happens to this operator L, where the algebraic type of this operator changes. For instance, eigenvalues of L collide. Okay, now the problem. So what kind of singular points can appear in this context? L is Nijenhuis, but singularities are still should be special. So, for instance, these are two examples of these operators. 0 is a singular point for both of them. So this operator is allowed in this context. It's a good singularity. This is bad singularity. So now the first result it concerns GL regular operators. As I said, GL regularity doesn't prevent collisions of singular points. So they may collide in very complicated way. The first theorem say that all collisions are allowed. From this context, in this context of GL regular Nijenhuis operators are absolutely perfect. Doesn't matter how singular points, so what kind of singular points, how singular these operators are, all of them are admissible. So each GL regular operator admit geodesically equivalent, geodesically compatible partner, which was very surprising result. However, so I need to say that single is important. If you want this metric to be positive definite, this is this other interesting story. So that what kind of singularities may appear in the case of positive signature, it's slightly different, but it's also that was done completely by Vladimir Matveev. So next So the next, so let me get back. Moreover, this metric G, geodesically equivalent partner, so can be described explicitly in terms of L, but you need second companion form. And this is, to my taste, this kind of magic and beautiful formula. So how this G and L are related to each other. The statement is as follows. So consider operator L. It is G L regular, so it can be reduced to second companion form, so like this. Now let's consider this identity here. So just identity where so P1, Pn are momenta, and so this identity is written on the quotient bundle. And the operator on the right hand side. So the operator on the right hand side. This is certain polynomial in L, so it commutes with L, and since it commutes with L, it's a polynomial in L with certain coefficients, and these coefficients h1 and so on hn are uniquely defined, and they are quadratic functions in P1, Pn, in momenta, quadratic functions in momenta. So it appears that the first coefficient in this expansion, h1, is exactly the metric which is geodesically compatible with L. It's, I don't know, it's fantastic news, I would say. So if you, by the way, if you deal with diagonal form of L, something similar, but you will get a very complicated formula obtained long ago by in fact. So next, how much time do I have?
I told you 5 minutes in the beginning.
Okay.
So I guess
Okay.
it's 5
No,
minutes.
that's fine. Then it's absolutely fine. So now the next question. Take an operator L and assume that it does admit at least one metric geodesically compatible with it. Next, we want to describe all geodesically equivalent partners for given operator L. And again, if we apply this theory about symmetries, then we will come to the following result, which also was very surprising first. Take L, Nijenhuis operator and G, which are geodesically compatible, and take a symmetry of L. Take symmetry of L and assume that the symmetry is G-symmetric, and take a new metric which is obtained from G and this operator M. So this is just a new metric. The statement is that this metric is still geodesically compatible with L. It's sort of, it's not surprising because M is closely related to L, and then we have this. So we know how using symmetries construct more and more geodesically compatible partners. And the second statement is that so if L is GL regular, and in this way we can construct just all of them. All geodesically equivalent partners are of this kind. So we have explicit description for partners. I repeat, even in the case when we consider singular points, still everything can be done. So this theorem generalizes into all the results by Sinyukov. So his result, his observation in this case can be explained in this way. Is if instead of M we consider just the same, the operator L itself, then it is true. So and then you can replace m with any polynomial of L or any function of L, but it appears that what you need to do, you need to consider all symmetries. And that was kind of unexpected. But now, yeah, why not? Now it looks natural to me. Now the quasi-linear systems related to Nijenhuis operators. So what I have here? So this is this is a way. So how, starting from Nijenhuis operator, well, you can construct sequence using certain procedure suggested by Franco Magri, actually. So he explains how, starting from Nijenhuis operators, which are very simple from the point of view of quasi-linear systems, you can construct more difficult quasi-linear systems which are still integrable. So then they are defined by these operators A0, A1, A2, and so on. So let's consider the PDE system generated by or defined by these operators. This system is known to be integrable, and so what I want to say. So if you have integrable infinite dimensional system, then to describe explicit solutions, usually people want to consider finite dimensional reduction. So they find certain subsystems finite dimension, so such that that we can integrate this finite dimensional system and in this way obtain solutions of this infinite dimensional system. So here in this context, so the following theorem holds true. So once again, so we have a system of PDEs. We know that this system is integrable, so we know that this system is constructed from Nijenhuis operator, now finite dimensional reductions. Take this operator L. Take the metric geodesically compatible with it. Take any geodesic and consider this geodesic as the initial condition for our infinite dimensional PDE system. So then, if you take solution with this initial condition, the statement is that this solution, so if you fix T1, Tn minus 1, and vary x, this solution is still geodesic of the same metric. So it means that the evolution defined by this the system of PDEs, this evolution sends geodesics to geodesics. And so why is that? Because these operators are in fact killing tensors for the metric G. For all metrics G which are geodesically equivalent, geodesically compatible with L, these operators are killing vector fields. And so one more interpretation of this result is as follows. So since we have kind of this, our PDE system describes some evolution on the space of geodesics, but what is this evolution? But this evolution is just nothing else that the geodesic flow. We have on the cotangent bundle, so we have integrable geodesic flows whose first integrals are defined by means of these operators of the scaling tensors A1, A2, and so on, An. And so then the value will tori, and there is the Poisson action of the group Rn, and this Poisson action is just exactly as the evolution in this infinite dimensional system. So I stop here. So there is one more slide. Maybe I will skip it. So there are some. There are some references. Okay. Okay. Let's say that maybe I will show one more slide after questions.